you have the mass balance part, you have the energy balance part, and you have the bio part, and so then you have enough time as a group to, because 27th you have to of December you have to start presenting. So I think I should put a. So is 11 o'clock okay? 11 to 1:30, 11 to 2 I will put it. So if you are tired, we will wind up at 1:30. Otherwise, 15th and 22nd. Normally we are doing 11 to 12 and 12 to 1. So let us just write 2 p.m., 11 to 2, and the entire course will then get finished by 28th, and bio portion will be finished on 22nd. Then we have one last week of reactive energy balance. So that would be perfect, right? Is that all right? I mean, there will be no time after I come back on the 25th of December, I mean. So I had said we have to make these classes up before you guys go on, before 28th of November. So shall I just post it and you tell me if you can see it? I'll just put it. If there's no objection to the time, then let us just put it, because we are sort of Monday to Saturday is taken, so we can't schedule it that time. So let me just 1 second. Okay, Sunday, let us see, the 12th or 15th. That's 22 November. Okay, I just sent the message. Did you get it? Just check if the dates are okay. I mean, we have only Sundays, right? But the thing is, you're free then from 14th to 25th, you're free in December. You don't have my class.
So we've received the message.
So just see. So when is the now after today? When are we meeting? Sunday. Just iterate it for me. I mean.
Yes, sir, just a second. So the message reads that the makeup class for the period December 14 to December 25,
Yeah.
Sunday 15 November, 11 a.m. to 2 p.m. and Sunday 22 November, 11 a.m. to 2 p.m.
22, 22nd is a Sunday, right? Is it
Yes,
correct?
sir.
Today is 11, 12, 13, 14. Oh, wait a minute. 11th is a no.
Sir,
Today
it's
is
a
12.
Sunday. It's Sunday
Today is
on
12, right?
22nd.
So 12, 13, 14, 15, 15th and 22nd. If you want, I can crash it in one day also. I mean, but then so that will be the whole bio portion in one day. I don't know. I just suggested it to divide it up, but
So maybe we could have it like on one single day, but in two portions, like in the morning and then short break, and then we could continue a
so
3 hour
what I
session.
suggest is let us do the 3 hours. Let us see how everybody is, isn't it? And then if you want it
Yes,
on the
sir.
same day, that is also all right. But okay. But then the problem is if we post it like this, it doesn't look. I mean, then we to change it at short notice is not a good idea.
Right, sir.
We have to make up those 6 hours or so. So, so the best thing is to do it this way. So let us meet on Sunday, and then we can do the at least half the bio portion. Then Monday I will be starting the reactions energy balance, and we need 2 weeks for 6 classes for that. That will be just correct. So we'll finish that on 27th, no, 26th rather, and then you are anyway off, and then I will only see you on the 27th of December. My leave and all is already approved, so this is all formal now. So we can actually we have very less possibilities to make up this time. Just we said we will do it 1 week before November 29th, so that's 22nd. But I think let us start on 15th and see how we go. And okay, so the thing is we were doing unreactive energy balance, and I said that we are no more interested in ideal systems. And I took steam as an example of a very non-ideal system. And since you had experimental data for steam, which is there in all the tables, and today maybe we should spend some time looking at those tables so that you know how to read that, because I mean you can be given any condition and you have to find out the specific volume or the specific entropy or the enthalpy or etc of any parcel of steam, and we should be able to read that from the table. So today I think what we need to do is to look at those tables so that you can use them, you know how to use them. Then the good thing is everything else you can use in conjunction with the equation you already know from thermodynamics. So for instance, depending on the sign convention, you had Q plus W equal to delta U for a closed system, right? First law statement. Or Q minus W, different books have it different. The chemistry and physics conventions are opposite. Or Q minus W is equal to delta U or delta H, delta U for a closed system. So let us say we have a parcel of steam in a container which is closed, and the container doesn't move and it's rigid, then there is no work that container does. So W becomes 0. So the Q is just equal to delta U. So if you are asked to find the heat changes, all you have to do is find the internal energy changes. So for that, you have to identify what state of the steam initially, say UI, and then the final state UF. And then the tables directly contain the enthalpy, internal energy, entropy, etc. in kilojoules per mole or per kg, depends on, you can do it specifically, or since you know the molecular weight per mole, whatever. So those are all tabulated, and we will look through that. And if by chance, let us say, it's generally tabulated in the tables for every, say, 10 degrees Celsius. So if you have a sometimes 50 degrees Celsius at higher temperature ranges, so if you have a temperature in the middle, you will interpolate linearly, right? So if you have an enthalpy value at 400 degrees Celsius and another value, let us say at 450 degrees, and you have to do at 425, you will take the value in the table at 400 and 450 and take the weighted mean. In this case, divide by 2, the sum of the two. That will be your enthalpy or internal energy per unit mass or per unit mole, right? So you can always do linear interpolation, because no table will give you at every degree or so. Okay, so linear interpolation you can readily do in between if you find a condition. And all the other things apply. For instance, if I have an isothermal process, then, and you know the initial temperature, you essentially know the final temperature. If it's isobaric, constant pressure, it fixes the pressure. If something is isenthalpic, it fixes the enthalpy. If something is isentropic, that fixes the entropy. So essentially, it is a way of specifying the initial condition, and you know what the final condition is, and you could be asked uh, something like enthalpy. Once you know the final entropy, you can look at that temperature and pressure, and you can find out what its specific enthalpy is, because that is also there in the table, right? But the question I left everybody with last time was a little trickier one. So what I want you to think on is, I said that there are two kinds of steams, right? One was we call saturated steam or wet steam, which contained two components, a saturated vapor and a saturated liquid, both in equilibrium with each other. And the entropy, enthalpy, internal energy of per unit mass of the vapor is much higher than that of the liquid. So that was a two-phase system. Then we all suppose we kept on heating it till the last dew droplet evaporated. Then you had a parcel of one phase steam, which we called superheated steam, right? So we said that you will have to specify temperature and pressure to fix the enthalpy and the entropy of this steam. So the only question is, suppose you don't know the final state of the steam, how will you know it's saturated or superheated? On what criterion will you decide that? So that's the question I left you with last time. Convener ji, are you all right? There's a message that we sent while you were missing. So, I hope you have looked at it. So we have extra classes, and we will be completing the bio portion in one or maybe two Sundays of three hours each.
Yes, sir. You mentioned that previously, I think.
I know. I mentioned it on first class because I know that I will be out. I will be out of town. So all that is now formally approved. So it's official also. So very nice. I'm glad you remember it. So because I wanted it right there in the first day, but it's good for you. Before 29th, you will be having the complete course. The bio portion will be finished. Today we are finishing the non-ideal, non-reactive thing, and then we will start from Monday the reactive energy balance. So that way we'll need at least 6 classes for that. 7. So depending on that, the 6 hours of classes, we will do 5 hours of bio, or that's why in a way I would like it 3 hours on Sunday and another 3 hours. So whatever is left off, depending on how fast, how slow, I can't anticipate. Okay, and so then you have a whole month, and then we only meet on 27th December. And by then, you have to have your project and all, whatever, as a group, you have to do some activity. 5 or 6 people, you can decide, you can have anything, a combination of mass and energy balance. You want to do a more bio thing, that is also possible, but there's less material available for the bio thing, but it's up to you. Okay, so everything you will have by 27th, we will be finished on with the whole thing. Is that all right, convener?
Yes, sir. Sir, one more thing I just wanted to ask. So, like after the mid-semester break, can we arrange some help sessions with you so that to like clear the doubts about our projects, if you have any?
Well, I will not be available actually.
So after the mid-semester
I am
break in
only
December.
available on a couple days after 29th. After that, my whereabouts, I mean, I won't even be here in, I will be completely out of station. It will
Okay, sir.
won't be so simple. But yeah, I mean, up to December 1st, 2nd, you can ask. But that
Okay,
is
sir.
like hardly makes any difference, right?
Yes, sir.
You are off on 29th, and because don't forget that I mean, this leave which I mentioned to you is 14, but I can always go on leave during the mid-sem break, and I am. It's just that the rule is that 10 teaching days. So 10 teaching days, so it's only counted from 14th. So basically from 1st December, I mean, I'm on leave also during the mid-sem break. So I mean, but that is right. So that's
Sir,
why.
but after mid-semester break, before 27th and after mid-semester break.
But I'm on leave, no? That time I won't be here. I mean, I'm only back on the 25th.
Oh, okay, sir.
Yeah, December, I am only back on 25th. So, and then there is little time. But yeah, in the next couple days after midsummer break, I am available. But that's about it. After first, I won't be reachable.
All right, sir.
Okay. So let us go back to that very interesting question. Uh, you correctly said that for saturated steam, if the pressure is fixed, its temperature is also fixed, which was what we were doing last time, that the boiling point, it's fixed for a two-phase system. So that was fine. But when it is two-phase, the two-phase disappears and becomes a single phase, then you need two variables to specify the state of the steam, the specific volumes and the specific entropies and the enthalpies, etc. So how will we identify in the table which table to consult? You see, there will be a separate table for saturated steam, which will be a composite of saturated vapor and saturated liquid. And I said that the mass fraction X of that will determine in a weighted mean the total specific enthalpy, entropy, specific volume. So X into the V times subscript G for the vapor plus 1 minus X into V subscript L for the liquid, and those you can read from the saturated table. That will be the total volume per unit mass or per unit mole per mole of the sample, right? Okay, but how do we know? How do we know if the steam is saturated or superheated? Another thing you can do, put the question in another way. Suppose now, take a look at any of internet, look for steam tables, preferably SI units. I'm used to all units, but there are many times they are available in the British units also. So just look at steam tables, because this is something you will need to solve any problem. I don't have to give you any properties, right? They are all there in those tables. So let us just see how to identify which table to use, where is that information located, and maybe we can try an example and actually find those values on the table. So can you find a whole copy of the steam tables? They are there in every chemical engineering and mechanical makes book, or chemical engineering thermodynamics books. They will all be tabulated at the end. So there will be two tables. One will be properties of saturated steam. Then there will be another table, properties of superheated steam. So first see if you can find them. Then let us first understand the nomenclature, and I'll show you how we read them. And we have to solve the problem of when we should use which table. And then we have time. We should definitely do an example so that the whole process is illustrated. what you need is first say saturated steam properties in SI units. Generally, 4 of these properties would be given. Small v, specific volume. Generally, it is in centimeter cube per gram. Okay. Then there will be a specific enthalpy. So that will be in kilojoules per kg. And all the new tables also plot you the specific internal energy in kilojoules per kg of the steam. So otherwise, you can always calculate the U from the definition of H is equal to U plus PV. You know the pressure, you know the specific volume, and so you can always, by subtraction from enthalpy, you can find the internal energy. But all the new tables have a separate column for internal energy per unit mass, and you also have the specific entropy in kilojoules per kg per Kelvin. So these 4 properties are listed along with the temperature and absolute pressure. Generally, absolute pressure is given in kilopascals. Generally, they tabulate it in the SI units in kilopascals. So see if you can see this, if you can obtain this properties of either it will say steam tables or properties of steam or saturated steam properties, or and then let us take a look. Then let us identify the range of temperature and pressure that is tabulated in these tables. It's several pages long. I mean, the entire steam table occupies 50 pages of textbooks, so because they cover a very vast range. So they start from, some point, I mean, they start from 0 degrees Celsius and the pressure is 0.5 or 0.6 kilopascals at that temperature, and then they go to very high temperature, the saturated steam. Let us see how much it goes up to. Kilopascals of 22,000 kilopascals. Okay, 22,000 kilopascals. And of course, the temperature will be about 374 degrees Kelvin. That is what it gives you. So the saturated steam goes from 0 degrees Celsius to a range of 375 degrees Celsius. And then the pressure goes from less than 1 kilopascal, so 0.6 kilopascal typically, to 22,000 kilopascal. This is the range of saturated steam that you want. See if you can find that. So this is two-phase steam, right? So you can look at the leftmost column. One should give you the saturation temperature and one should give you the pressure of the system in kilopascal. Temperature is equal to what the value tabulated in the first column. You only told me that you need to specify only one parameter, right? So everything is fixed. So suppose you are given 60 degrees Celsius. The kilopascals of total pressure is in kilopascal is only around 20, and that's fixed. So see if now at that temperature and that pressure, tell me what is the specific volume of the vapor in cubic centimeter per gram.
So could you please repeat the question?
Right. So I just said find the tables, and suppose I look at the saturated steam table. Suppose I gave you 60 degrees Celsius as the saturation temperature, then you can find the pressure of the system, which is approximately 20 kilopascals. Can you locate it, is what I asked. And once you have located this, and it will always be 20 kilopascals and nothing else, because there's only one freedom degree. And now I said, what is the volume in cubic centimeter per gram of the steam of of the vapor part, that is the saturated vapor? What is that specific volume is my question for the condition of temperature and pressure that we just discussed. You have to read
So
it from the.
it's 7.65 kilo centimeter cube per gram.
Right. So it's something like 7,700 centimeter cube per gram. That's because
Yes,
you
sir.
saw there are two. Actually, there are three columns, but the middle column for the specific volume you can ignore. That is just the difference of the two columns on the left and the right. So the saturated vapor column gives you the volume of the vapor in cubic centimeter per gram, and the specific volume of the saturated liquid, which is very close to the density of liquid water, it is 1.017, that is so many centimeter cube per gram at 60 degrees Celsius. Okay, and the middle column, generally called evaporation, is the difference between 7678 minus 1.017. So we don't need that. So okay, similarly at that 60 degrees Celsius, the saturated vapor has an enthalpy of 2457 kilojoules per kg, and the saturated liquid has a very low internal energy of kilojoules per kg of 251. Is that all right? Can you locate that as you go along the row that you just
Yes,
now
sir.
identified for 60 degrees Celsius
Yes,
and
sir.
20 kilopascals? So essentially, you have all the information of enthalpy, entropy, internal energy, and volume all per unit kg. Okay, at the desired condition. Very good. So this is the saturated table. Now, if you look at the superheated table, you will have a similar table for single phase steam. This is called superheated steam. So in other words, you keep on heating till the liquid disappears. So then the enthalpy of the system will, of course, be much higher, because now the liquid is contributing nothing. So similarly, look at the superheated table, and now you will have to specify both the absolute pressure in kilopascals as well as the saturation temperature. The saturation temperature is fixed from the saturated table, but now you have to specify the actual temperature of this single phase steam, which will be much higher than the saturation temperature that you read from the first table. So that is how you will identify if the steam is superheated or not. In other words, first you will look up, let us say you know the pressure. So for the pressure, in our case 20 kilopascals, you looked up, you saw, okay, what is the saturation temperature for that pressure in saturated steam table? It was how much? It was 60 degrees Celsius. Now let us say the temperature is higher than 60 degrees, then that steam has to be superheated, and you have to now look at the superheated tables. Naturally, because the two-phase steam can only exist at 60 degrees Celsius when the pressure is 20 kilopascals.
So there is a region enclosed in this table. What does that mean?
Superheated table.
Region.
Yes, sir. Enclosed by
You can
line.
also get graphs. You can also get graphs. So I mean, we can also do the same problem by looking at graphs, but then the problem is you don't get a numerical value. So don't look at the graphs. You can also find graphs on the net. But what I'm saying is you have to look at numerical value tables. Since it's a calculations course, you will need the values. Otherwise, वो graphs से आपको पढ़ना बहुत मुश्किल हो जाएगा. So maybe you're looking at a. So you will have at least the superheated table will be at least 30-40 pages. You know, it will start from a value. Let us see. See, it starts from 1 kPa and it goes to a absolute pressure to an absolute 20. Superheated steam tables will go from 1 kPa to 22,000 or 21,000 something kilopascals. What it will give you in bracket is the saturation temperature of the saturated steam. Suppose, for instance, you had 15,000 kilopascals absolute pressure. In the superheated table, there will be a just below it the saturation temperature within parentheses. So that is 342 degrees Celsius. But now let us say our temperature is 400 degrees Celsius. So now keep going on the along the x-axis and identify in that matrix 15,000 kilopascal and 400 degrees Celsius. So that will be the first, second, third, fourth, fifth, sixth column in the table. That is because every 10 degrees you have one column. So 350 to 400. So sixth column you will at 400 Celsius, you will get at 15,000 kilopascal because you have to specify both now. Just specifying one will not solve. So it gives you four values: 15.6, which is the centimeter cube per gram in specific volume, 2,740 for the specific internal energy, 2,979 naturally enthalpy will be higher by PV term, 2,980, and it gives you specific entropy of kilojoules per kg per Kelvin of 5.89. That is the value you have to locate. And this also tells you when you have to use the superheated table. Whenever your temperature that the problem gives you is higher than 342 degrees for 15,000 kilopascals, the steam has to be superheated. So this goes that the temperature range at 15,000 kPa goes from 360 degrees all the way to 650 degrees Celsius. So every 20 degrees you have a column. So, and in between you will linearly interpolate. Suppose you have 420, 440 and you are 430, you will interpolate between the values of the two columns. So that will be the specific internal energy, enthalpy, entropy, etc. of that single phase steam or superheated steam. So only if the temperature is higher than the saturation temperature, then we know it is superheated. So let us work out a specific problem. It will help you a lot. Let me randomly choose something. Okay. Wet steam is given at 230 degrees Celsius. Wet steam is given at 230 degrees Celsius and it has a specific volume of 25.79 centimeter cube per gram. 25.79 centimeter cube per gram. Find its enthalpy and specific enthalpy is what is meant per kg, of course. Find its specific enthalpy and specific entropy. So it's a saturated steam. Go to 230 degrees. If you go to 230 degrees, that is exactly there, 230 degrees, it will give you the pressure in equilibrium, which is 2798 kilopascals. Fine, but they haven't asked you the pressure. It gives you the saturated liquid and saturated vapor values. Saturated liquid is 1.2 centimeter cube per gram and 71.45 centimeter cube per gram for the vapor. Okay, 71.45. But what the value given to you is 25.79. So find the quality, as it is called, small x, the mass fraction, which is vapor. Because you know the total is 25.79. So if that is x, or that is the quality, so the quality of the steam x multiplied by the vapor phase specific volume plus 1 minus x times liquid phase specific volume must be 25.79. You know both the values at from the table at 230 degrees Celsius. So find this quality for small x. At 230 degrees, wait a minute, 230 degrees, at 230 degrees, V subscript G is 71.45 centimeter cube per gram. So that x into that plus 1 minus x into the V liquid, which is 1.209, must equal 25.79 centimeter cube per gram. So x is the only unknown. Find that quality. That's what it is called, the mass fraction, which is vapor. Find that. What does that work out to? So 25.79 is small x into 71.45 plus 1 minus x into 1.209. So you will solve for x. Now, the good thing is the same quality applies to enthalpy also, right? I mean, it applies to all the properties. So you found it for the specific volume data because that was given to you for the partial of steam. Now use that x and using the H subscript G and H subscript L values, find the specific enthalpy for that steam. And similarly, you can do for SG, SL and X times XG and so on. 1 minus x times xl will give me the entropy in kilojoules per kg per Kelvin. Now, suppose I kept on heating this steam such that the last drop of liquid disappears. And let us say I specify you and I say somehow I keep the pressure the same. So then what you have to do is you will have to look at 2800 kilopascal in the superheated tables. So let us find 2800 kilopascals. 2800 kilopascals. Now at 2800 kilopascals, let us say my temperature is 400 degrees Celsius. Now I can ask you, what is the new enthalpy per unit mass? So you'll have to go to 2800 kilopascal, find the 400 degrees Celsius column and read the value of the enthalpy, which works out to be 3236 kilojoules per kg. That is because now the steam has a temperature much higher than saturation temperature. Saturation temperature is only 230 degrees at 2800 kilopascal, but now the temperature is 400, so of course its enthalpy will be much higher per unit gram or whatever than the saturation. Basically, you can essentially, the innovation here for us is that we are no more confined to ideal systems. The same kind of things, if we had the data, I prefer water because the data is easily available. But similarly, data is available for polar gases like CO2, NH3. But it's not available for some of the more esoteric systems. So if all of these are available, we do not need to assume ideal gas behavior. For instance, if I asked you an internal energy change, you do not need to assume any gas loss. You do not need to even assume that internal energy is only a function of temperature. It could be a function of pressure also. It could be a function of all parameters. And if the values are tabulated, you can get exact values depending on how good the data is. Okay, and the usual thermodynamic Q minus W is delta U. So you can find the heat change because it's W is 0 in the case I just gave you of the wet steam, because nothing is moving and there is no piston type device here. So all you have to do is find delta U. And delta U, you will find, U1, it was saturated. Let's say finally it was superheated. You will read at 400 degrees Celsius, you will read the superheated volume and then find the delta U of that per unit mass. And suppose the mass of the system is given, you will multiply by it and get the total internal energy. Okay. So essentially, we have to now draw to a close on the unreactive energy balance, and we have to now do a little more complex subject of a single reaction energy balance and then multiple reactions energy balance. And this is going to take me 2 weeks of classes, and we need 6 hours for the bio portion. So Sunday I will start the bio portion. Let's see how we progress. And Monday onwards, I will go to the reactive energy balance. Okay. So the new thing you have learned is that in the unreactive energy balance, we are not making any assumption of ideality. And you can consult the tables, which you can always bring with any exam, etc. And essentially, I don't need to give you the properties. I don't need to give you van der Waals parameters and anything, in fact. So everything is there and you can get exact answers for non-ideal behavior. That is because the properties of steam and water have been perfectly experimentally determined to the decimal to 1 decimal place with 0 degrees as the reference. Okay, I'll now meet you on Sunday at 11 o'clock, same time as as the Wednesday and Monday classes, and let us look at the bio portion, which we have to begin afresh. So let us see how fast or how slow we are. I cannot anticipate right now, and based on that, let us continue. Okay, and Monday I will start you the reactive systems, and we will be finished by 27th with that. Okay. All right.
Thank you, sir.
Thank you very much, Ashish.